So today we're going to be talking about cameras, views, and viewports. These are sort of our ways of looking at the world of our games. Last time we talked a little bit about ray casting and line intersection. That will be used for assignment 4. And cameras and views will also be used for assignment 4, sort of in a minor way, but they will also play one of the major roles in the project. Do you have a quick question?
The assignment Dropbox for the project GitHub link also says 30th.
Okay, so just to repeat that, the correct due date for the project proposal is the 4th of November. So I didn't update that for the spreadsheet. I just fixed it in the spreadsheet, but I will also fix it there. So if you're currently online, just send me an email so I remember to do that as soon as I get back to my office. Thanks. Okay, yeah, so there's an extra 5 days there. I didn't want to make it due on the same day as assignment 4. That's why I gave a few extra days for that. Yeah, so we'll be talking about cameras and views today, which will be used in assignment 4 as well as the project. Just a quick note before we get started that I made this post a few days ago about important project information. And if you have not yet found a partner for the project, just send me an email. And tomorrow morning, I'm going to go through all the emails that I got. I think I've gotten 3 or 4 so far. And I'm going to assign those people to groups in first come, first serve basis. So it's working out so far that there's probably exactly 1 group of people who haven't been able to find a group yet. But if you send me an email about that by tomorrow, then, or by tonight, I guess, tomorrow morning, I'll be putting you in a group. Okay, let's get started. Okay, so game cameras and views. So video game worlds, just like the real world, they're often much, much bigger than we can display all on the screen at once. So like in the real world, we can only display a subsection of the world at a given time, right? I'm standing here, there's this huge infinite universe that is surrounding all of me, but I can only see this much in front of me, right? There are walls occluding my vision. My eyes can only see to about, I guess, 170 degrees or so. I can only see so far due to atmospheric effects, etc. And so the part of the game world that we can currently see is called the view into that world. So this lecture is all about, first I'm going to go a little bit into 3D game views. Even though we won't be implementing those, I think it's a good idea to actually start with that idea because it's a little bit more intuitive than 2D game views. Even though 2D game views are mathematically simpler, they can get surprisingly complex. So to mathematically describe our desired view of the game world, we often use the concept of an in-game camera. So just like a camera in the real world, intuitively we can define the location of the location of the camera in the world and where it points to. So if I took a real camera and I put it, say, up in that corner, pointing towards a particular location, and that camera had a specific focal length or zoom level, it would be taking a picture of a certain part of that world. So similar to real photography, this will determine the final view that we see. There is a great video here. So there's 3 videos in this class. I will put the links to, well, all the links are in the slides, which you have access to, but I'll also put them in the description of the video. And we're not going to watch the first one in class, but we will watch video 2 and 3 in class. Maybe not all of it, but a majority of it. But then I'm going to cut those videos from the actual video because I don't like playing other people's YouTube videos on my YouTube video. So we won't watch this one, but please watch this one. It's a very interesting video that goes into why cameras are difficult, how they affect gameplay, and stuff like this. So in the 3D game world and in real life, we have this concept of a camera, and that defines how we actually get to visualize our game, which is arguably the most important part of a game, right? Have you ever played a game where just the camera sucked and it like really affected gameplay, and you know, you're in this tight space and the camera, I just can't see anything, or this boss is able to do things and I can't react to them because the camera is just bad. So the camera is something that often gets overlooked, but is possibly the most important part of the game because it allows you to visualize and play it properly. So in 3D space, what we typically do, these game APIs and graphics APIs have the concept of a camera. Typically that's like some sort of class in the API, and what you can do is you can position the camera in 3D space, so you give it an X, a Y, and a Z location, and then typically there will be two other parameters. One will be this vector typically called the look at vector. So the camera is in a particular position, yes, but it's also facing a particular direction. And then based on where it's facing, the third sort of parameter, now you could have many, many different parameters, but the next main one would be the equivalent of an actual camera's focal length or the level of zoom or field of view, right? So if your field of view is higher, you'll be able to see a wider image. If your field of view is shorter or less, then you'll be able to see less of the image, but typically more zoomed in. And so over here we can see, you know, here we have a camera and it looks like it's following this little duck around. And so in a lot of games they will have, or in game engines, they will have APIs that allow you to specify, okay, here's the camera and here's where it's looking at. And you could say, for example, a follow camera might have the camera positioned in a particular place, and then the look at vector, the endpoint of that, is just a particular NPC or the player or something like that. So here are just a few different types of camera views that you can get in 3D space, and of course there's probably an infinite number of them, but these are sort of the typical tropes that you see in most video games. So this first one down here is a fixed camera position with a variable camera look at, and variable meaning that the place the camera is looking at is changing, but it just happens to be at the center of this entity here. So if I put my little mouse laser pointer on the center of that, you can see that this camera is always looking at that particular NPC. So that would be great for some situations, but also not great for other situations, because I'm sure if you've ever used a camera like this in a video game, it's actually kind of hard to run your character around in a game if the camera is in a fixed location, because you're getting further away from the camera, so you're getting smaller, your movements mean something different, etc. So one of the most popular views you'll see in a 3D game is this sort of older, over the shoulder or behind the back view of a player. So here, in this one, the camera itself was fixed in space, looking at a particular object. But here what we do is we're still focused on a particular object, but now the camera is moving along with that object from behind. So typically what you do in order to implement a camera like this is you would have some sort of, you'd do some testing, some play testing, and say, okay, we want the camera to probably be this far or 2 meters behind the main character. And so you'd take a vector, you'd point it, you'd figure out the normal vector. We talked about that last time with the cross product. So you'd figure out maybe the normal vector to the person's back, and then you'd move the vector so that or you'd scale the vector so it was 2 meters in length, right? And then it would always be behind the person's back and pointing at that person. Up here, we see a completely static camera where the camera is static and what it is looking at is static. So these is sort of like a movie camera, I guess, where you're watching a cutscene or something like that. It would be quite disorienting to try and play a game where you could say run off the screen, for example. And showing my age here, but hopefully some of you have played like Ocarina of Time for the N64. There are many scenarios in that game where you both encounter this static type camera as well as this type of static follow type camera, as well as this type of camera. So different cameras can be used within the same game depending on the context, etc. And down here, of course, now we've got different types of VR headsets. And those VR headsets, what they do is they use different motion tracking, accelerometers, etc., in order to try and simulate your point of view as if you were in the game world. So if you move your head, then the camera will move. And so this is mimicking like one-to-one what you would actually be looking at if you were inside the game world. And so 3D cameras can be pretty complex, but they have the benefit of being incredibly intuitive because we've all sort of encountered this sort of thing in the real world. 2D game cameras, on the other hand, they're not really cameras because we just have this like infinitely flat plane that we're looking at, right? So these concepts of like field of view and stuff, typically, so in cameras like this, they use pretty decent actual camera lighting, not necessarily lighting, but vision physics, right? Things that are farther away are typically smaller, things that are closer are bigger, things are occluded by specific angles and stuff like that. Whereas in 2D cameras, even though this area over in the corner may be further away from this imaginary camera, it's actually the same size as the thing that is the same distance or a closer distance to this imaginary camera. And I forgot, but I think it's called an orthographic projection, where this one is called a perspective projection. So this is like an actual perspective, a real world perspective where those properties hold. And this one is just picture that there's a view that we can see. There's no actual camera with conical physics and all this stuff happening. But what we would do then is, instead of defining this camera in a 3D space that doesn't exist in our 2D world, we're just going to define the area of the 2D world that we want to see. That's it. It's pretty simple, right? So we just define the rectangle of the part of the world that we want to see. It couldn't get much simpler than that in terms of the mathematics, because you're just saying, okay, here's my top left, here's my width and my height. But it turns out that 2D cameras can almost be more complex than 3D cameras because of the challenges faced in 2D games that aren't necessarily there when we talk about 3D games. So something that may be unintuitive is that the camera can be used as part of the gameplay as well. So I forget which game this is. I'm going to show a lot of different games. I probably should have put the names of the games on the screen. But in this one, as the player moves a little bit close to this treasure or this secret area or whatever it is, the camera actually zooms out to show that, hey, this is a thing that you may want to pay attention to. So there are really interesting things that you can do with cameras, not just show, okay, it's always static, it's always centered at the person, etc. So what I'm going to do now is I'm going to show this quick video, and this video has very loud music, so I apologize for the immediate sound that's going to happen, but I'm going to turn it down. And this will show really nice examples of 2D camera types, and then I have slides going into more details, about those camera types. Okay, so it turns out that there are, like, who has ever played a 2D platformer and thought about that kind of stuff, right? It just either feels good or it doesn't feel good. But it turns out there are lots of interesting ways to construct those cameras. And I'm going to edit the project information document later, because what I said in the document was you have to implement 2 different camera views. And what I meant to say was 2 different camera views that we have not done in the assignments. So you can't just implement like the same camera view as in assignment 3 or assignment 4. So basically what most people do is one of these like box trap type views. And it's very interesting how much of an effect that has on your gameplay when your screen is just not like shaking because it's not following the player all the time. So in terms of implementing these things, in SFML, a view is sort of like a window into another world, right? So if we had a window in this classroom, I used to be able to point to a window and give this example, but that window is literally a view into the outside world, right? So that has been set up by some parameters, and you can see through that and see some of that outside world. So it kind of is a window. So an SF view, that's how you would define it in SFML. Just type SF view. It's a rectangle representing a 2D camera that you can use to specify which pixels of a game will be drawn to the window. So changing a window's view does not alter the underlying entities or sprites' positions. It simply changes where in the window that they are drawn. So by changing the view, we can change what part of our game world is shown to the player. So just think about, if you didn't have access to this SF view, how could you mimic a camera that actually moved around in the world to show you different part of the world, right? So one of those ways, and I've actually done this like a long time ago in the past when I had no idea that views existed, not with SFML, but with OpenGL, was to move everything in the world instead of move the camera, right? So take every single entity in your world and just move it to the left. And that makes it look like you're moving to the right, or the camera is moving to the right. And that's something you could do. You could shrink everything in the world to make it look like you're zooming out, etc. But that is quite cumbersome and quite expensive, right? And taking every single entity in your world and moving it around, when all you would have to do here is just change the rectangle that you want to be viewed. So the important thing here to keep in mind is that even though your window might be a specific size, that's just the window, right? You can define any part of the game world that is seen through that window. So here is some sample code from the tutorials for SFML. And again, apologies, this is from version 2 of SFML, so the syntax may have slightly changed, but I don't think it's changed because it uses rectangles. So here we have our render window. That's the window object that we use in our project. And then we have a view. So what we could do is initialize, for example, a view to a rectangle located at 100, 100 with a size of 400 by 200. So what this is you will be looking at this rectangle of the game world no matter how big your window actually is, right? So this view does not need to match the same size as the window. It doesn't even need to match the same aspect ratio as the window. And if you define a view that is not the same aspect ratio or the same size, then you're effectively zooming in or zooming out on that content. And if the aspect ratio is off, then you may actually skew things a little bit. So it's pretty typical to make sure that no matter what area of the world you're viewing, you still want to have that same aspect ratio, whether it's square, 16 by 9, 4 by 3, whatever. Make sure the aspect ratio is the same so that the objects still have the same height to width ratio and they don't look squished. You can also rotate the view, which looks pretty trippy when you do it. There were a few old Super Nintendo games. I know it's outside of your scope, but Super Nintendo introduced this thing called Mode 7 graphics, and it was basically rotation and scaling on the game screen. And it looked pretty bad in some games, but games like Pilot Wings and stuff where you're mocking 3D-ness by scaling and rotating 2D-ness, it actually worked out pretty well. So you can rotate things, and then what you can do is you can set, we'll talk about viewports in a bit, so let's ignore this line of a viewport. And then you can apply that view to the window. So you've constructed a view somehow, you have that stored in an SF view, and now you say window.setView, and you pass it that object. Then you could render some stuff, and then what you can do, and this is actually a big tip for your project, is that you can set a different view and render again. So why would you want to set two different views and render with two different views in your game world? Well, let's say, for example, you have your entire game world, your top-down RPG, you're just looking at one small section of this huge world you've constructed. But now what you would like to be able to do is, so whenever you draw something in the world, you're drawing it to the world coordinates, and then you're looking through your window at those world coordinates. But sometimes what you would also like to be able to do, if you want to draw like a user interface or a heads-up display, let's say we would always want our health to be displayed in the bottom left corner of the window, right? So what do we want to do? Do we want to figure out where in the world we should draw that health so that it always matches up with where our window is looking? No, we don't have to do that. So what we could do is we first set the view to the view of the world that we want to see, render all the stuff in our game world, then we can set our Windows view back to its default view. And then that's after we've rendered everything, so that now we would start rendering with the default view. So now if we said draw something at 0, 0, it would always be up in the top left corner of the screen. If we said draw it at window width over 2, window height over 2, maybe we want to draw a little cross here, so now it would always be in the center of the screen. So that way we can render stuff with respect to the world and look at it, but also render stuff with respect to the window and look at it. And we don't have to go that extra step of trying to figure out where in the game world we would need to place something in order for it to be in a specific part of the window. So hopefully that makes some sort of sense to you, is that when you render something, it is rendered with respect to the current view. And if you reset the view and then render again, you can have it, for example, be displayed with respect to the window rather than the game world. So in this example here, can anyone just put up your hand, don't just yell it out, why would I draw the game world first and not the text on the screen first? Yep.
If you draw the text on the screen first, when you render the game world, it's going to cover the text.
Exactly, right? So the answer there is that rendering is done in order. And so if we drew the sort of heads-up display text of our health, and then we drew the game world, then the game world would be on top of it and we wouldn't get to see it. So that's why we typically set the world view first, render the world stuff, then set the default view and render the stuff we want to render with respect to the window. Okay, so this article is great. I hope it's still up. I actually didn't click it today. But this is, it's called The Theory and Practice of Cameras in Side-Scrollers, and it's basically a huge written article with a lot more examples than that video that we just watched. So I've taken some of the images from there, and I'll talk about them in some of the slides. But first, we want to talk about the default view. So the default view, and this is what we did for assignment 1 and assignment 2. This is the SFML default view. And the window, by default, if we do not set a view, comes with this, this default view. And essentially, we are looking at the part of the game world that starts with 0, 0 up in the top left and width height down in the bottom right. So we are looking at the same portion of the game world that is like identical to the window, right? So pixel 100, 200 in the game world is always rendered at pixel 100, 200 on the window itself. So this is a one-to-one mapping between the game world just being put onto the window, which is sometimes what we want and sometimes what we don't want. And so the view never moves. And if the view never moves, then the whole game world has to fit into our window. Just keep in mind whenever you're doing one of these static default views. It works well for certain arcade-style games or board games, but it's very limited in what it can do, and it's, you know, most modern games wouldn't have a view like this. But here, for example, board games, if you were making a chess game in SFML, then you probably wouldn't worry too much about world coordinates versus window coordinates and setting views. You would just draw stuff to the screen, right? Because that whole chessboard can fit on your screen, and it's very unlikely that you're going to be like zooming in to see the action in the chess game or panning over to other chessboards and stuff. Other older arcade games, anyone who might be more than 20 years old can come up with an example of a game whose view never changes? Any other game you know? Yeah?
Breakout?
Which one?
Breakout?
Breakout. Is that like the hitting the blocks?
Yeah.
Yeah. So arcade style games like that, you've all played a game like this, I'm sure, where you have a little paddle on bottom and there's a ball that bounces and it hits some bricks. Something like Donkey Kong is one screen. Now it'll change to a different level, but all that level is on one screen. Pac-Man, games like this, they all fit on one screen. So they would all use a default view. The next type of view, I would say in terms of simplicity of implementation, would be a position lock type of view. So here, for example, I'll just put my mouse cursor over that, and you can see that the camera's always centered on a particular entity or feature of the game. 99% of the time, that's going to be the player, right? So here in this game, we have a car driving around in this world, and the camera is just always fixed right on that car. And whether that's in the center of the screen or the top of the screen, whatever, doesn't really matter. Here it's in the center. Actually, it's in the center of the left part of the screen because this game has some sort of heads-up display being drawn over here on the right-hand side of the screen, and it looks like maybe a mini-map here being drawn as well. And so this works best in games with smooth motion overall, and position lock really starts to shine when the character or the entity that it's following is really small in comparison to everything that's shown in the view. In fact, I think that the character here probably isn't even small enough for this to work well. It's still like a bit of motion sickness, right? Like it's just too much moving around. And so I would think that there are better examples of this, and I'll have a better example in a second. Also keep in mind that any of the techniques that I'm about to show can be implemented in one of two overall ways. One is sort of like instant or auto lock, where the camera is locked instantly on the target. And the second one is when some sort of smoothing is applied to that effect. So if we want to lock on to a moving target or to a new place within the level, then instead of just instantly going there, the camera smooths a little bit. So I'll have examples of both of these in a sec, but just choose which fits best for your game, right? If you think that instant lock is okay, then use that. If not, then maybe try some smoothing to make it less jagged. So here's an example from Terraria. Any Terraria players? Anyone ever played this? Okay, a couple people. I used to play a bunch of this game. And here, the character by default is just so small in comparison to the world that this sort of auto lock camera, have the player in the middle of the world, is just good enough, right? So we can see that this works a lot better, in my opinion, than that other example where the car was like maybe 2 or 3 times this size, because the world is moving in such a way that it's not so jarring to your vision. It's not inducing that same sort of, that feeling, I don't know how to describe, it's just a bit weird. Here we have an example from Super Meat Boy, which implements a smoothing camera lock. So the camera always wants to be centered at Meat Boy, but you can see here that as the player moves, the camera takes a little bit of time to catch up to center exactly on the player. And depending on the game, depending on play testing, user feedback, etc., QA, you may want to implement one of these things over the other. I played a lot of Super Meat Boy when it came out, and I really like the way the camera works in this game. I think it works well for a game in which you are moving both vertically and horizontally a lot. Next, we look at something like the original Super Mario Brothers, or what we have for assignment 3, where we just have a horizontal scrolling view. So, oh yeah, I forgot to mention that a view like this is one of the easiest, other than the default view, it's the easiest thing to implement in SFML, because you can take a view in SFML and just call set center. And so if you set the center of the view on the player's location, for example, then you get this effect for free. The only caveat there is that if all you do is change the center, then the size of the view will remain the same. It will just be centered on that player. So that's a really easy thing to implement. Next we have, like I said, the horizontal view. This is what we have on assignment 3. And this is where we just have the player being followed in the x-axis. So these sorts of views and these sorts of games, it's very fascinating if you look back at the history of video games, and over time, as more and more genres of video games were able to be made because of increases in technology, right? So like early computing systems were not able to display color, right? And then they weren't able to display graphics or sprites, but then they were. And then scrolling, how do I implement scrolling? How do I move all of my pixels on my computer screen to the left by 1? Is that what I do, or do I have some sort of weird memory buffer system? It's really interesting if you go back and look at that, but that's a bit of out of scope. But what I'm saying here is that the reason I am using old games as examples for this is because this was sort of by necessity in old games rather than by design in old games. So here we have this Kung Fu type game where you're just like moving from left to right, knocking people out with your sweet kicks. But what this can do is if we're just locked on, then this can lead to kind of really jerky movements left and right. And it's only really useful when you are locked to a particular horizontal or vertical section of your world, right? So here, for example, this game has been designed so that you're never going high, you can't see higher than one screen at a time. And then at the end here, this little thing happens where you walk upstairs, it's just like an autoplay cutscene, and then you're on the next level where you walk left to right. Okay. Now this idea can be taken and applied not only horizontally, but of course it can be applied vertically as well. But there are actually some games that scroll at like angles. So they're still kind of in straight lines, but you're scrolling at an angle. So over on the left here is this, I don't know if it's Adventure Island or Wonder Boy. They have the exact same sprite, just one is Nintendo and one is Sega. But here you can see that this is actually moving down and to the right as the player goes on. And over here we have, I don't know which game this is, but it's a 3D game engine, but it's sort of a 2D game stuck within that, like I guess they call it like 2.5D type of game, right? And here we're scrolling in a particular direction and the world is actually rotating as well, but just ignore the 3D part of that for now. Next we have this idea of a box or a trap view, which we saw in that video. And so what you're going to do here is you define a box around the player. And again, like the video said, instead of following the player, the camera follows the box. And the box only moves in the game world if the player has reached the boundary of the box and wants to sort of leave the boundary of that box. And so this is useful for games that have like side-scrolling games where you're jumping a lot or there's a lot of back and forth motion or fighting. And so what we can see here is that for a lot of this motion, the camera isn't actually moving, which is great because the more the camera moves, the harder it is to actually perform those actions in the game. And as humans, this sort of movement is not great. We don't process it well, and it's easier to do things when the camera isn't moving. But the camera eventually has to move in order to see the next part of the level. And so, in my opinion, this is a really great balance between those two things. So up here we have an example where we have just a standard 4-sided box trap centered at the middle of the screen. But down here we have another gauntlet type game. I don't know the exact name of the game. But you can see here that it's sort of the bottom right is in the middle of the screen. So how would you differentiate between these two in your game? Well, it turns out I think this particular level in this game, the box traps could be defined on a level-by-level basis as well. So I think in this level, the player actually starts kind of up in the top left of this world and is always moving to the right and down. They're never going back up and they're never going back to the left. And so by placing the box trap more to the left, what happens is as you're going to the right, you get sort of more foresight into what's coming from the right. You get this entire half of the screen to see the enemies that are coming from the right. Versus in this game, you would only get about a quarter of the screen to see what's coming from the right. Similarly, since the motion here is mostly right and down, you also have half of the screen to see what's coming at you from the bottom. Or maybe if you're dropping down, I want to be able to position myself on this platform or something like that. And so that's one of the design decisions that you would make in your game when it comes to not only what parts of the screen do I want to see, but in comparison to where my player is, what parts of the world do I want to be able to see more of, right? And so this, again, is something that we've probably never thought about until it's so bad that it's annoying, right? All right, next is from the game Fez, which has a 3D world, but you only ever interact with it in a 2D way, but then you can actually change the view in the game, and so you sort of explore, yes, you can walk around in 3D, but only in one plane at a time. And so this is such a unique game in terms of its gameplay mechanics and its camera, where the camera is actually a gameplay mechanic in this game. It's so important that it turns out to be like the selling point of the game, this is really cool. And here you can see that there is a 3-sided box trap, so you can kind of, it will follow the player up, but not down until it hits the box trap down. And also, if you can sort of notice it when the player goes down, is that there's also smoothing implemented on top of this box trap. So when the player's feet go through this, you can see that it comes down to meet it rather than just being locked at that player's position. So now we can just start to see how complex these things get, right? There's also position snapping. So position snapping, instead of locking, is sort of built-in smoothing. And so here we have some ungodly combination of these different camera views where it is auto-locked in the X direction, but has smooth or position snapping in the Y direction, where as the player moves the camera vertically, the camera will move until this line hits the player's feet, right? So again, this is a design decision where they have chosen, okay, we always sort of want to see, you can see it's off center, so it's more to the left. So this means the game is probably moving from left to right most of the time. And we are also showing more of the bottom of the screen, which means that we would probably want to have more downward movement in this game because we can see more of the downward stuff. Here we're sort of jumping up in this little GIF, but yeah, where the player is on the screen, you can see matters. And this has a smoother overall movement than just camera locking, but again, you can see how crazy this can get. Another thing that was shown in the video is called platform snapping. I think that, so this is Super Mario World for the Super Nintendo, and I think it has one of the best cameras in any 2D platformer of all time. And so this is like the position snapping that we just saw, where as the player moves up, the camera will gradually move up. But this doesn't follow the player exactly. There are places marked in the game as platforms, and then when the player reaches those platforms and lands on them, the camera will snap, not instantly, but it will move smoothly towards those platforms. And so here, this works really, really well for this sort of vertical level. And we'll show an example at the end of just how complex the Mario camera can be. This is another example where I think this is Rayman, maybe, where instead of just having like box-like geometry for the game, they actually can move up these sort of smooth slopes on these platforms. And of course, the GIF cuts out right before it actually gets to that. But it's the same sort of thing, where you have platform snapping instead of player snapping. Next would be camera zones. So camera zones are not identical. These are like whatever you could accomplish with a box trap, you could do with a camera zone as well, but not every camera zone could be accomplished with a box trap because it's not always moving when the player leaves the zones. The zones sort of define this arbitrary behavior that your camera would then follow. So for example here, when Mario, and this is like exactly what happens in the original Super Mario Brothers, when Mario reaches halfway across the screen in the X direction, the camera will lock on to Mario horizontally. But when the camera goes to the left, because the original Super Mario Brothers doesn't allow screen scrolling to the left, so if you walk to the left, instead of having to get all the way back to the middle for the camera to be following you, as soon as you get to this line, the camera will start moving and then it will follow you once you get to the middle line. So there's a slight difference there where the camera will start moving when you start to get toward the middle, but not exactly at the middle. This is an example from Metroid for the NES, which acts more similarly to a box trap, but I'm calling it a zone here because it's not fully a box, like it's not completely boxed in. But this one acts much more like a box trap, where the player is sort of trapped between these, over here horizontally, the camera will only scroll when the player tries to exit this, this zone, and over here vertically when the player tries to exit that zone. Next, and now I try to remember how to explain this every year, but it's kind of crazy. And it involves if Mario happens to be to the left of this line and then starts to move to the right, it will start moving when Mario gets here, but then snap when it gets here, and like the opposite for over here. But it's incredibly complex to like describe, but it ends up being a really cool smooth motion in a game where you value moving to the right as much as you do moving to the left. But what this does, unlike that earlier gauntlet example, is that when you are moving in a particular direction for a long enough amount of time, it will always give you more of the camera in that direction. So when Mario is moving to the right, it's, for the most part, it's snapping at this line, and when moving to the left, it will snap at this line. But only after Mario has like past a certain amount of distance, if that makes sense. So what this does is no matter what direction you're facing, you will be given more of a view in that direction. So you're not always moving to the right, so you don't always want to have this bias on the camera moving to the right. Here are more examples of cameras where, what is this? Is it Defender? Can't remember, but my uncle used to own this arcade machine, so he'd be disappointed if I didn't know this game. But again, cameras in which you can combine different zones, different things. So over here, these are just two zones where if you're moving to the left or right for long enough, the camera will smoothly catch up to you, and then the line will be just behind you. So again, this is a very high-paced action game, or high-speed action game, lots of stuff going on. So they want to give you as much camera real estate in front of where you're going in the direction of motion as possible. And over here is a similar thing, but it also implements, whereas this game never goes, it never moves vertically, right? So you can get away with no vertical snapping because we don't need to move vertically. But over here, it also implements this smooth platform snapping when we get to a new platform. So lots of different ways that we can move the camera around in 2D games, and I want you to sort of pick one of those and implement it as your main camera for your game. And not all of these things have to be done for platforming games, right? These sort of camera traps and stuff could also be top-down action RPG style games as well. But camera zooming and focus are also a thing. So over here in one of the Mario games, is this Yoshi's Story, I think? Not sure. The camera zooms in and out depending on what's happening in the gameplay. So something appears on the screen like a bomb that you're supposed to be able to pick up, and so the camera gives you a nice little hint. And this also does this sort of same thing with fighting games, which I'll get to in a second, where the camera zooms out to try and keep you and the boss on the camera at all times, right? So depending on other factors within the world, the camera's view is actually moving in and out. And whether or not that's a good thing is up to you and your players and developers. Over here is another crazy camera where it like locks and zooms in on features in the game. So, okay, I'm supposed to do something here or collect this item or meld these things together. And there's a lot of different parameters here on the camera that I'm not even going to attempt to explain, but it results in some pretty cool effects on the camera. Camera windows are also a thing, especially in fighting games. So the camera window can grow and shrink as players get closer or further apart. And this is really useful in games like fighting games where you can't give an advantage to any of the things on the screen. So this is like a two-player fighting game. You might be in some tournament somewhere. Maybe, okay, why would you let one person run off the screen but not the other person? Like that would give an advantage to someone. So here, this is really interesting because the gameplay mechanics affect the camera. Meaning that like if you have someone like Dhalsim in Street Fighter with really long legs, you know, you wouldn't want maybe their moves to be able to reach all the way across the screen, or maybe you have fireballs with a certain speed and you want a player to be able to react to that. So the camera affects gameplay mechanics, and the gameplay mechanics affect the camera as well, because you want them to be able to back up to maintain some distance strategically, but you don't want them to get so far apart that you can just run around and avoid the person altogether. So this is a really interesting case where you have both the gameplay mechanics and the camera in such tight lockstep together, where if you changed the camera of the game, you would actually be changing the balance of the game itself, in my opinion. Camera shake is also a cool effect that some people do, where, and again, this could be accomplished either by moving the camera or by moving everything in the world. But oftentimes it's much easier to move the camera than to move everything in the world. And when something happens in the game, like you hit a POW here in Mario Brothers, or over here, when this like large boss entity gets on the screen, whenever it falls, like there's a screen shake or something like that. It's the people who have implemented screen shakes on their assignments and their projects like have done it surprisingly well, and it adds so much value to the game just by moving the camera around a bit. The video also showed this, where you might have some like RPG type game. You have this whole huge map. And one of those types of views that we saw was called a grid view. And in a grid view, we are going to define a grid on our level. So for example, here, I can chop this level up into, this world up into a grid. I'm not doing it exactly. I don't know who can do this with a mouse exactly, but I certainly can. So there's my bad grid. And basically what you do is, whenever the player enters, or whenever the player is walking around, and you will be doing this for assignment 4, you'll figure out which grid, I don't know, a screen, I guess you could call it, a grid screen or a screen grid, whichever grid position they're in, that is the part of the world that you'll show. And so while they are in a particular grid cell, you will lock the camera to show that entire grid cell. But while they're walking around within that grid cell, the camera won't change at all. And then, if you teleport around, you'll just show that different grid cell. And this, whatever grid cell you're in, the size of the grid, etc., is completely a game design decision, not a game programming decision. So a view in SFML can be defined in different ways. You can either define it in terms of top left width and height, or with a float rect, or you can have two vector 2fs. So whichever way you think is a little bit easier to do. This means that the same view can be accomplished in different ways. Oh, sorry, these are actually two different things. So this one is a rectangle defining the top and the top left x and y, and the width and height. So this would be like 0, 0 all the way down to width height. The second one is not the same. It is actually different, where you define the center point x and y and the width and the height. So this one might be more useful if you're trying to implement a following view on the player, because you can just define the center. And the top one might be much easier to implement like a room-based view or a grid-based view, because you're finding the grid and you're just sending the camera equal to that. So this means that you could define the same view using both methods, right? So x, y, width, and height could be, okay, now I have to get the center of this, which would be x plus width over 2, y plus height over 2, and then width height. So these two different lines of code would produce the same resulting view. So using the top left or the center may be more convenient based on the different type of game that you're making. So this would be sort of the first way to define that, where you have x and y in the top left and the width and the height. This is the rectangle-based way. The same with this one. And this is what we'll be doing for assignment 4. It's probably easier for the grid-based view to implement this rectangle view. But the other view we're implementing for this game is the follow camera, where you just center on link here, or not link for copyright reasons. And to do that, you would use the second type of view, where you don't change the width and height at all, you just change the center location. So there's lots of different things you can do to a view after you have the object. You can reset it, you can set its center, you can set its size, you can move it. So this will like, you're adding a delta to it. So without changing the size, you can just move it over rather than having to get it and add it and then reset it. The view can be zoomed more toward the center if you want to, so you can set the zoom. Z less than 1 is closer, greater than 1 is further. You can also rotate the view, which is incredibly disorienting. The reason it's so disorienting is because depending on how you have implemented your controls, so say let's say this is the actual game, if I move up, I will actually be moving like this on the screen. Right? Because I'm moving up in terms of game coordinates, but then I've rotated the screen to draw it. And so this actually, there are some games, like these sort of Kaizo intentionally hard games like Boshi or Camilla, these types of games, will actually rotate the screen or rotate the controls to try and make it harder. Please, for the love of God, don't do that. Your games are going to be hard enough already. But I'm just saying that it's something interesting you can do. One thing I saw once on a project was that whenever they went to the next level, they just, over the course of maybe 2 or 3 seconds, they rotated the screen, and it was like you were going down a toilet or something like that. So they rotated and zoomed in, and then rotated and zoomed back out to get to the next level. And something that takes you 5 minutes to implement like that just adds so much polish and niceness to the game. And it's like surprising how many subconscious marks you get from me when you just show that little bit of extra flair or whatever on the game. It goes from like, okay, we did the bare minimum to get our 50 to like, we actually care about game programming and we did this. The last thing I'll talk about, I think, are viewports. So views define which part of the game world will be drawn to the window, right? So that is like the dimensions of the window when you're looking outside. But a viewport defines where on the window the view of the world will be drawn. So that's almost kind of like where on the wall the window is, okay? So for example, I could draw only on the left-hand side of the window if I wanted to. And you're saying, why in the name of God would you want to do something like this? Well, by default, the viewport is the entire window, okay? But we can change it. And we'll show an example of why we might want to change it. So the viewport, at least in SFML, it's not defined in pixels, but instead as a ratio of the window size. So at least in SFML2, this is how you did it. So you set viewport as a float rect x, y, width, and height. X, y, that's the ratio of the window for the top left of where the rendering is going to start. And then width, height is the ratio of your size of your render. So here's an example of this. I'll go to the pen. So this up here says float rect 0.25, 0.25. What does that mean? It means that our viewport is going to start 0.25, or 1/4 over from the left, that's the x, and then 1/4 down from the top. That's this one and this one. That's where it's going to start. And then the size is going to be half the screen in the x direction and half the screen in the y direction. So it's half the screen over and half the screen down. So that's how we define where the viewport is inside the window. Now, you may think that, like, why would you ever just want to have that be smaller? And the answer to that is that you can have multiple viewports in the same window. So think about that. You could have multiple windows to the world inside one game screen. So you can use this for many different things. So, for example, it can be interesting for gameplay or for game mechanics, for example. You could have two-player split screen. As long as you're like, you could have two players on the same keyboard, or if you hooked up controllers, you could have two-player split screen like this, right? So let's just try and define these viewports from this. So viewport 1 would start at x0, y0. It would be 0.5 across, and it would be 1 down, right? And we're using half the width, all the height, starting in the top left. The second one would start at 0.5 in the x, and it would start at 0 in the y, and it would also have 0.5 width and 0.5 height. Let's see. Yeah, so that's what I have right here. So you could have, who has played a local multiplayer game before? Anyone? Was it GoldenEye? Hopefully. Like Mario Kart probably is the most modern example of the most played local multiplayer, where like my wife and I can sit down and both play. Sometimes it's split screen left and right, sometimes it's top and bottom. I remember specifically being at such a competitive like sleepover LAN party like back in high school with my friends playing GoldenEye, that because it was on the same TV, one guy played and he was under a blanket and had half the screen taped off with the blanket so that the person playing on top couldn't see where he was in the screen. It's hilarious, like how competitive that got. But yeah, GoldenEye dates me a little bit. Or what you could do is you could create a mini-map. So for example, you could render, and by the way, each viewport has its own view. So you don't have to display the same thing in each viewport. So over here, you can see this is the viewport over here, and that's probably like, okay, 3/4 of the way over, 0 down, and it's 1/4, 1/4. So that's how you would define that. And just 1 second on the question. A lot of people end up doing the mini-map for the second view in the project, and that's fine. One thing that I really liked from one game is that you were trying to find the princess or the prince or whoever in the level, and what you could see is that the second viewport up in the top corner was like focused on that entity as it was moving around. So you couldn't see exactly where it was. You say, oh, it's like it's near the bridge or whatever because it was walking there. So that was cool. Did you have a question?
Yeah. So here, like, there's a black outline around the mini map.
Yep.
Is that just there by default, or did you have to add that somehow? Because I noticed with the split screen example too, like if it went all the way to halfway and the last one started at exactly halfway, there shouldn't be like a black line, or they would just be right on top of each other almost.
Yeah, so the question, just repeating for the microphone, was this black line that we see here, both in that split screen and as a border around this, those have to be added separately through whatever rendering that you're doing. So you'd probably, after you rendered stuff, you could just draw like a black strip down or like just a box a little bit bigger before you render the second viewport. But that's the reason for that is that if you have absolutely no cutoff, it's kind of disorienting because you don't really see where the seam is. Now you can tell because stuff is moving around, but it's just for humans to be able to interpret it better. But that's a good question. No, those don't appear by default. So viewports, like I said, they can be used to create interesting or useful views for gameplay. And something else that I've seen is you could use this if you had like a driving game or something, like old driving games were all 2D and like, you know, the road was there and you just steer left and right and you'd go on the road. But maybe there's like a missile coming from behind you. And so one old game that I can't remember had a rear view mirror up in the top as a separate viewport. And so you could see the cars behind you because your car was at the bottom of the screen. So you could see what was in front of you, which is great for gameplay because you want to be able to see what's coming, but also this little rear view mirror that let you see what was behind you. You could also do something like an enemy perspective, etc. There's two main ways that we can implement these sort of camera types. One is like the ECS sort of data-based way that we've been doing it, like have an enum for all the different camera types, and then we would have a camera system where it says, if the camera type is this, then do this. Or we could have a camera class that has a bunch of different derived cameras. That's how some systems do it. But this is what we're going to be doing for our assignment and for our project. It's just now here, where we were using strings before, now I'm like, okay, this is how you would use an enum for this. So we'd have to define all the different camera types, and down here, we just have an if statement or a switch saying, okay, if this is the camera type, then inside here, we would say, okay, let's define a view, and then we set it to the player, or we set it to the window, etc. But other things might have this sort of thing where a camera class might take in a reference to the game engine so that it could see the window and change the window as it views, as it wanted. The next thing, just the last thing that I'm going to show a bit of this video. Please go watch the entire video after if we don't have time to watch the whole video. But one of the things that you have to do on the project is called parallax. And parallax is kind of difficult to show, or it's kind of difficult to explain without just showing a nice video, like an animated example of it. And rather than spend like hundreds of hours trying to recreate something as good as this video, I'm just going to show you this video. So let me just check if I have anything after this. No, so after this will be the end of the presentation. So the video will probably cut off now, but please actually go watch that, go down in the description or in the slides and see the URL to this video.